Sorry for the interruption. So, so we apply uh, the divergence on certain vector field, and then if it is if the value is less than zero, right? So that means that it's actually converging to a certain point, right? So if the value of divergence is greater than zero, that means it's going out of the surface. Okay, so that's actually how you look at the flow. Now, here are the demonstrations. So you see, in the first case, uh, so in the first case, you see, this is your vector field, right? So this vector field could be your magnetic field, or it could be your electric field. Okay, and this is the region, right? And this operator we call divergence. We will later, the do the derivation, how to do it. Now you see the important thing, the value is zero, right? So what does it mean? It means that you see the number of flux line, this is entering and this is leaving. This is entering and this is leaving. So the number of flux lines entering and leaving are same. Therefore, the divergence is zero. In this case, you can see the number of flux line entering and leaving are same. Therefore, the divergence is zero. In our previous discussion, we saw that the uh, the gradient operator, which we use del on t, right? That's what we call the gradient operator, right? So t is scalar quantity, and the resulting answer is actually vector, right? Now we use divergence. So divergence operator is del dot E, right? Now the difference is, here T is scalar and the answer is vector. But here the E is vector and the answer is scalar. So first quantity tells us the change, right? The second quantity tells us the divergence, convergence, or you can say flow. It tells us that how the quantity is entering or leaving or flowing, right? So we use this operator to actually model the flux or electric field line passing through certain region or area. Okay, so this is very important. As you can see, all these above example, the surface integral is zero. I'm going to discuss this. Over some portion of the surface, the component is positive, whereas on the other portion, the component is negative. You see, this one, because it's entering and this is leaving, at one position it's positive, another position is negative, but the overall sum is actually zero because the entering and leaving is same. That's actually the purpose of the divergence. Now you see again, one property, the final answer is scalar field, right? So that is positive in some region in space and negative in other region, depending upon in or out. So it also provides the output in terms of a scalar field that represents the sources of the vector field, that tells us whether this source is, flowing out or taking in the flux. Let's see, this is your input, right? So you see that the flux is coming out from this region. There could be a sphere, there could be a metal sphere or any other conducting sphere that has some charges, and the flux is, or the electric field is going out of the sphere. So in order to apply the divergence, we can use this formula, del dot E, that we are going to solve now. Now, first look at the physical demonstration. You see, that's the point, minus 1, 1. So you see that minus 1 is here, comes here, and 1 is here, right? So, so this point, actually, you see the divergence is maximum, right? So that's the result of this vector field. Now you see that at this position, the flux line, they're coming out. Okay. So when you apply this, you would see that the flux at this region is maximum. Now, you can also visualize in the 3D, and you see that there is some flux at the corners, but that is very, very small. See, the value of divergence is very, very low. And at the center, at the peak, that represents the main, the source of flux, where the flux is actually passing. Okay. Again, if you have many sources of charges, for example, there could be a negative charge, there could be positive charge. You see, these three spots, they represent the highest point where the flux has a maximum, outreach. So it's going outside. So you can get these three regions. So remember, in our previous lecture, we discussed this as a scalar field. That was our input. Remember, I'd give you the example of topology of the Earth, right? So how the different mountains are placed, and then you apply the gradient. Now this is opposite, you see. Now this is the result actually. That's the final outcome, right? So you will see that this is just values, 1, -1, +1, 5, 6, 0, 10, 8, 9, whatever it is. So these are all the scalar values that tells you that, okay, at which location actually your flux is maximum or minimum, or actually there's no flux, right? So you can combine these inputs and outputs to see. So input is now vector and output is scalar. Now you see that. So these are the two important, the outcomes. So sometime in exam, I ask, okay, what's the difference between gradient and divergence, right? So you can find here. So gradient produces vector field that indicates the change, and also the input of a gradient must be scalar value. And the second point, divergence produce scalar field, and the input should be a vector field, right? So the functionality looks like input and output are totally opposite. Okay. Now let's take this topic from our main notebook, and then we see how to model the divergence of a vector field in terms of a mathematical formula. Okay, so we will try to find out the relationship, how to apply this operator. So you can see we have a charge q. Usually this setup is similar to a sphere ball that is charged. So how to charge the ball? You know that if you connect a ball of sphere with some high voltage, right? So the charge, it develops at the the terminal, right? So every terminal of a voltage source is built up of charge, either positive or negative. So you can consider it as a positive terminal of a voltage source. Now you see every charge, or the number of charges, when they are scattered or when they are deposited on a certain volume or sphere, you would see that there are electric field lines that are actually emitting away from the body of the sphere. So for simplicity, you can just consider a single charge source that is emitting certain electric field lines. And because uh, the electric field lines, they are randomly, right? So they are randomly positioned away from the position of the charge. So if you look at the outer surface of the sphere, you will find out that majority of the electric field lines, they are going away from the surface of the sphere, right? That means they are at perpendicular. You see this N stands for perpendicular, normal. You call it normal vector. That means perpendicular to the surface. So uh, in order to find out the flux or the electric flux, or we call it flux density, right? In order to find out this, you would find out that we need to take the surface integral, E dot ds. So we use actually three types of integral to model the behavior, or we find out the quantities. Remember, I gave you the example of a work done. So remember, work done is equal to force times distance, right? So force time L, or force time the S, whatever you like for, but we know that L is for the length and S is for the area. So we just represent L. Uh, in physics, we use this term, right? So this is length and this is our force, right? So work done is equal to force multiplied by length or dot product. That's very simple, right? But actually, if you have this type of surface or length, right? So let's say you are following this path, right? Then how to find out this one, okay? Now, remember, at every position, you have a length vector, okay? At every position, you have a length vectors. So how to find out the work now? So we do that F dot dl. We take the single integral, right? That's how you do it. So this is for the path that is, in a random position. So you know the equation of the line, right? And then you do the integration. That's what we call the line integral. Okay. But in our physics lectures, we learned that it's very simple. You multiply length and force vector, but that's possible only when the length is straight, right? If the length is not straight, then what you have to do is you have to take the integral. So remember what actually integral does. So it actually divides this length into small vectors that are straight enough, right? So you can model any irregular path with small and straight vectors. Now f dot dl1, f dot dl2, f dot dl3, f dot dl4, sum up all. That's exactly what every integral in the universe is doing, right? So that's the formula, or that's the purpose of integration, right? Now, this is for the length integral, or more specifically, we call them line integral, right? Is it clear? Okay. Now, we know that not all the quantities in sciences or in physics or in mathematics, they follow the length formula. All those formulas that actually uses the length multiplication, you can model them with the line integral if the path is not straight. Okay. So can you remember any quantity that uses area as a multiplication? Any quantity. You see, for work done, we need force times length, right? Do you remember any other formula that not uses length, instead it uses area? Electric flux. Electric flux is equal to flux density is equal to the electric field times area. So if you find out the flux or electric field lines passing through certain area, right? So what you do, you take the vector E multiplied with the A area. Similarly, magnetic flux phi is equal to B Tesla multiplied by area. Remember, if you know the area of the coil, right? You know the magnetic field, multiply it and you get the flux Webers, right? So there are certain quantities that uses area, and this one, flux density, is one of them. Now, if the area is straightforward, just like a rectangular coil, it's very simple. Length multiplied by width, right? It's very simple. If the coil is circular, it's very simple. Flux multiplied by pi r square, area of the circle. It's very simple, right? How about if the area is something which is the surface of a sphere, of a surface of a cylinder? Then how to solve it? Then we go to our previous thing. We look at these patches of a cylinder and the sphere and multiply it. Okay. We know the area, differential area, remember? We know the differential area in the table we discussed in the last lecture. Okay. So we use that one and apply the double integral, and then we get the area. Okay. So there are certain quantities that actually uses the surface integral. Okay, so let's say flux is equal to E dot ds, right? Now this area could be like this. It could be a small patch on the surface of any shape. So you multiply E with that ds, and then you get a whole flux. Okay, but because this ds is small, then we can use E dot ds, right, by using double integral. If it is rectangular, we use xy. If it is cylinder, we use two limits, r or phi or z, right? Remember in our previous table, we discussed this, okay? So we can use any of them to find out the flux. Similarly, in the next upcoming slide, I will show you that there are certain quantities that actually use volume integration to find out the quantity. Remember in our previous example, we learned here, you see, there are certain quantities that require volume integration, right? So charge is one of them. So if you know the charge density, right, this is charge density, then you can find out the charge by using the triple integration. Okay. So we have line integral, we have a surface integral, and we have volume integration. Okay. So let's come to the main point to discuss the divergence. So we use the divergence by del dot E. Okay, previously we using the gradient, which is del of t. Remember, that's the gradient. There is no dot inside. Remember, this dot does not mean dot product. It's just a convention to make it different from the gradient. It's not a dot product. Okay. Okay. So that's the operator, what we call the divergence. Sometimes people write div, or sometimes we write del dot e. Now, what's the difference? This t in gradient is scalar, but this t in divergence is vector. Okay, that's the main difference. Now, you see the formula is same, right? Can you spot out some differences of divergence with respect to gradient? Can you recall the gradient formula and compare and tell me the difference? Please look at the gradient formula and then tell me what are the differences. Yes, yes. So this end product is scalar because it does not have unit vectors, you see. So there could be some answer, you can add them together physically. That's the one difference. Another difference. Okay. Another difference is we are not using the whole vector here. We are only using the x component. In the gradient, we take the whole function t. We take the derivative t 3 times along x, y, and z, right? But here, because it's already a vector quantity, right? This E is vector, right? Right? So vector has three parts, x, y, and z. We take x part for x derivative, y part for y derivative, z part for z derivative. That's the main difference. We don't use the complete function because E is vector now. In gradient, T is not a vector, it's a scalar. It does not have x, y, z. It's a scalar function. Okay. So these are the two main differences. Now, apart from this, you can also read out this definition. This is important. This definition is important. Plus this this difference is important. Okay. So these are the differences between scalar gradient and the vector divergence. Okay. Now, yeah, sure. Why not? Why not? Why not? I can write here. You see, uh, del of t. This is called gradient, and this is temperature. We call scalar field. Okay, and the answer is del t over x. So that's the main difference. We have a complete function here, t. Another main difference is it has a unit vector. Why? Because the answer is vector. Okay. Now look at the differences in the divergence. So this is divergence. So this is vector. Okay. And this is x component, right? And the final output is scalar. Okay. So these are the key differences you can compare. Okay. In terms of exam, you must have knowledge about these two formulas. Okay. Okay. And their differences. It's very, very important. So for all the exams, they have included these divergence and the gradient. Okay. So another thing, if the value of divergence is positive, because the scalar value, as you know that the value is final output is scalar, right? So scalar mean if E has a positive value, that means that your small volume can be considered as a source. Source mean it's supplying the flux. Okay. If the value is negative, then it's considered as a sink. That means flux is going towards the center, right? If the field is uniform, then divergence is zero. Sometimes I ask students, okay, this is a vector field, find the divergence and comment on the answer. It's very simple. So you just apply this formula that we will do later. And after applying the formula, you look at the answer. If the answer is 15, then you have to comment because it's positive, so it's a source. Sometimes the answer is zero. So I would ask why the answer is zero. Then you can tell me that, okay, because it's a uniform field. The flux entering the volume and leaving the volume are same. That's why the answer is zero, right? So that's the reason. So, all the scalars can have zero. So these three reflect three different phenomena related to the source. Okay. Now, look at this. Although this is a derivation, but I don't expect you to memorize this. Okay. Please listen very carefully. So I do not expect you to memorize this, but at least you should have an idea. how the divergence is computed from any phenomena. So this actually combines all the previous concepts into one formula. Okay, listen. This is a cube. Okay, so these green lines, they are actually electric field lines. Okay, so there could be some pathway, there could be some imaginary box, there could be imaginary surface. Let's say this is a cube, right? So it's easier to solve, right? So if we take a sphere or we take a cylinder, then the coordinates are quite complex. Okay. So for simplicity, we will consider this x, y, z plane. See, we all know that the sphere, it has 6 faces, right? Right. So let's say the flux is entering from this side and leaving from this side. So we have 1, 2, 3, 4, 5, and 6 faces. Okay. Now, for simplicity, just look at, we have E vector. Okay. So E is our electric field. So this is our E. This is our E. Okay. So remember, any vector has 3 components because it's a Cartesian system, right? So E has some component along x-axis. It is value, maybe 10, 5, 6, whatever. Okay. And then you can write this. Right. So this EX is value. If I write a vector, then I can write like this: 2x plus 3y or plus 4z. It's same thing, right? Okay. So this EX is actually any constant value along x-axis. That's how we represent vectors, right? We already know, right? So that's a kind of a vector. So EX is the component along x-axis, Y is the component along y-axis, and EZ is the component along z-axis. Now, because this flux is passing through this cube, some part of the flux is entering or leaving in phase 1, entering or leaving in phase 2. Similarly, all the 6 sides of a cube, there is some flux, right? Either it's entering or leaving. Some sides will be entering, some sides will be leaving, right? There may be possibility that leaving and entering are not same. Okay. So we want to analyze this situation. So if we want to find out the flux, remember I told you that for flux or flux density, this is called flux density. So flux density is F1. We are interested in F1. F1 is the phase 1. Okay. So I assume that you already understood this. You see, this cube, it's placed as the 0, 0, 0 or x, y, z. That's considered its place x, y, z. Now, because it's all the x, y, and z are same. So this distance x plus delta x. What is delta x? Delta x is actually a length along x, maybe 2 centimeters. So this point is delta y plus delta y, maybe 3 centimeter high. So this point is z plus delta, maybe 5 centimeters. Right? So if you place it x, y, z, then this point to this point, this is the point, this point, this point, right? Now we have different phases. We will apply the flux from phase 1. Can you see this small patch? Right. So this is the phase. Let's say the flux is going this, some part is here, 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 and we are interested in this quantity. Right. Remember, because this is the area. Right. Area is very simple. Because just length into width is the area. That's what we learned in the Cartesian system. Right? So we multiply this area along with the E vector, and then we will get the flux. Okay? Area multiplied by the electric field. Now we solve this one, and we see that flux is equal to E dot ds. M1 actually stands for normal direction. every flux that's going like this or this, we will not consider. We only consider the flux which is perpendicular to the normal direction. Right? That's why we write this n. Uh, and you see this minus x, because if you see the F1, if you see F1 is along minus x direction. You see, this is x direction. X direction is there, and phase one is there. So this direction is minus x1. So minus x plus x up. This is y. This is minus y. Actually, you can take any random direction. It doesn't matter, right? So we have 6 directions actually. X minus x, y minus y, z minus. Doesn't matter which phase you assign which value. It's normal. So flux through phase one is equal to the electric field times the area. Now, E, as I mentioned, is a vector. The normal direction is minus x, right? And what's the area? Of course, along this area, we have dy dz. That's very simple. We learned in the coordinate table, right? You look at the coordinate system, right? So along this, the area, the length is dy and dz, height and the width. So you multiply this, and then you simplify. You see that because y dot x is 0, correct? Z dot x is 0. So these two components will cancel out, and we will get only x component, and we will get Ex dy dz, right? So we write 1 here, right? That actually tells us that the flux that is passing through phase 1. Okay, so Ex, the 1 stands for, because of phase 1, right? We're doing integration on phase 1, right? So we use 1 here to make it different from the other. So we will get Ex1 dy dz. Okay? Let's say dy and dz, the distance is 2 centimeter and 3 centimeters, so 3 times 2 basically the area. Okay? So that's how we find the flux. So you might have seen that why we are doing this is we are trying to find out the flux from all the 6 sides, and then we are going to add them together to see what happens. Okay. Now, if you apply the same method on phase 2, right? So you will get exactly the same answer, but you will get Ex2 because that's on the phase 2 side. So you use the limit 2 because we do not have values. In the last question, I have the full problem, right? So along with values, here we are just trying to derive something. And then instead of Ex1, we have Ex2 because it's the same area on the opposite side of the cube. So we use y and z same values. Okay. Now, these are 2 different answers. One is for flux 1 and another is for flux 2, right? We can use some mathematical trick here to transform this Ex1 in terms of Ex2 or Ex2 in terms of Ex1. So do you know the difference between these 2 things? So one of the quantity is going here, another is quantity is going here. The only difference between them is delta x, because they are delta x separated, which is exactly the width of the cube, right? Now, if you are familiar with the Taylor series, right? So Taylor series will give you the expansion of any function that has a small increment, right? I have uploaded the reference the formula on the Blackboard as well. So we can right here. So you can see the Taylor series expansion, right? You can have Taylor series on both sides and also on the one side. So this is for the both sides, right? X plus delta x and y plus delta y, right? So you can approximate any function with small increment, right? And what you will get is this function. Plus other series. So you get the function plus derivative of a function along with small error or small increment plus second order derivative plus third order derivative plus fourth and keeps on going. That's an approximation. But if we consider the first two term, we can get almost more than 98, 99% approximation. Okay. So we use the same concept here. So ex2 in terms of ex1 is equal to ex1 plus the first derivative multiplied by the change. That's the Taylor series. So it's helped us to approximate the function that is delta x apart from each other. Okay. Now, what is the benefit here? Because if we add this one into f2, x2, put this x2 here, right? Then you will get f2 in this term. And now you add this thing and this thing, and you will get very interesting result. That is, take the derivative of ex with respect to x, and you have delta x, delta y, delta z. Okay, so this is the flux of f1 and f2. Now you don't need to do it again 4 times. Do it with 3 plus 4 and 5 plus 6, and you will get again, the correspondingly symmetrical results. Now add all of them. Okay, now we are talking something very, very interesting. Add all of them and you will get this formula. Okay, so the total flux, this is total flux. So the total flux is E dot ds, right? This is called surface integration. And this round signal means closed surface. That means it's a closed surface, bounded by, the starting and the end points are same. Now, the total flux is now equal to some mathematical operator multiplied by volume. Actually, it's not volume, it's a change in volume, right? A small integral volume. Now you see this thing inside here is actually divergence, right? So we can now say that the divergence is equal to this one, right? Now, if you have already figured out this one, now we have one of the most uh, widely used, interesting, and important theorem, what we call divergence theorem, right? So I ask you to randomly think about these two formulas and try to interpret in your language. Then I'll explain to you what does it mean. So far from our demonstration, right? So you can take the previous results into consideration as well, and also look at this thing. This is very important and useful thing. We will also solve it with some tutorial problem. So on the left hand side, you see this integral and the v below, right? That means volume integration. That means three integrals: length, width, and height. Okay. Then we have divergence of vector field, right? This is equal to surface integration of E dot ds. That means flux. So did you see any important transformation here? In your thought, what do you think this formula says? So this is our total flux, right? This is total flux. Now, if you want to find out the total flux from any surface, right? In our case, we have a cube, right? So cube has 6 surfaces, right? Phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6. right? So you add up surface integration or flux from 6 surfaces and write down the answer. It will take some time, right? So you have to do the integration 6 times, right? Because there are 6 faces. Every face has the flux. Write down the answer. And on contrary, you try to compute the divergence of the E and do volume integration one time. The answer is exactly same, right? That's actually the physical meaning. In mathematics, people call it something, how can we convert volume integration into surface integration or surface integration into volume integration? Okay, so that's very important. We will also uh, look at the Gauss law, which is Maxwell first equation, and we will try to answer some questions using this. Okay, so it's one of the useful tool for converting integration over a volume and over the surface enclosing that volume and vice versa. So you can convert it, right? Let's write down some of the important properties here. So that's what we call volume integration. So this is our vector field E, right? And that's called the divergence, right? And that's called the surface integral. Actually, it's a 2 integral, right? This is 3 integral, right? That means that x, y, or z. This is 2 integral, right? So this is the, or this flows sign mean flows integral, right? Now, this side means that you take 6 integrals because there are 6 sides, right? So how many combinations it will make, right? X, y, y, z, and x, z. And similarly, on the other side, you also have these 3. And then add these 6 integrals 6 times. That means that f1, f2, f3, f4, f5, and f6. And the answer is very, very simple by using 3 lines. You take the volume integration, that's it, of the divergence. So that's the reason divergence is very important. Okay. Now, is this clear? Any question regarding this divergence theorem? Okay. Let's do a small question regarding the divergence, and then after that we will do very important question regarding the exam. Okay. So if you are given the divergence, so you are given a vector field E. Remember, this is a vector. Okay. So vector is 3x square, 2z, and x square z. Remember, this part is Ex. Why this is Ex? Because it's along with x. Okay. This part is Ey. This part is Ez. Now, if you remember, I told you that in exam, we asked you to compute the gradient, which we did in our last lecture. Sometimes we ask you exactly the same question, right? To compute the divergence. So first you need to tell me what is divergence, write down the formula. And then use this function and find out the answer. That's it. So this is the formula of the divergence. Okay. So that's the divergence. Remember, this thing is very, very important. It's not E, it's Ex. In gradient, we have complete function here, but in divergence, we have only X component. Okay. Now, this is Ex, so we put 3x here. Ey is 2z, we put it here. Ez is x square z, we put it here. Okay, then take the derivative. Derivative of 3x square is 6x. So 3 and then multiplied by 2x, that is 6x. Okay. Similarly, derivative of 2z with respect to y is 0. Right? This is tricky. Usually, I give this type of question in midterm, and many students make mistakes. They should know that derivative of y of any other function except y is 0, because z is constant with respect to y, right? So this is 0. How about x square z? Now z is constant, right? X square is multiplied, so constant should be outside, and the final answer is x square z. There should be a mistake here. Probably there's no z here. Okay, make it correction. Okay, there's no z here. Or no, so sorry, it's correct, it's z. So derivative of z with respect to x square z is, yes, so x square, so z is constant, so you have x square. Yeah, it's correct. Now, final answer is x square plus 6x, because the question also asks you to evaluate at 2 minus 2, 0. So we put this point and the answer is 16. Correct. Now this is positive answer, right? So we can assume that the flux is something going away. Okay, or number of flux line n is greater than leaving. Okay. So if you take the gradient, sorry, divergence on a complete surface, you will get this answer. So it's a positive value. So positive value means that the outward flux is higher, right? Now, also look at these. These are for the revision. These are your practice. So please listen here. The divergence can also be applied on cylindrical and spherical systems. Okay. So these are for practice only. So you see that the divergence in spherical system is quite complex here, right? But you can still use it. This is not for exam. Yeah, because divergence on rectangular component is okay. Okay, but for exam we do not ask to apply on spherical or cylindrical, but we can ask this in during the assignment. Okay, so you should know how to solve it in other systems, but in exam we do not ask this question for the other coordinate systems. Okay. No. This question, you are given a vector field E equals to, right? So that means you have a vector field E A R. So A is a constant, R is the radius, and the direction is R. Can anybody draw this field? Do you know how to draw this field? Because the direction is radial. So it's a sphere, right? So this value is R and the amplitude is AR. See? So the amplitude is AR, which is constant, and capital R is the direction. That means a sphere that has radius. calculate the flux of E. So we know that the flux is equal to surface density, surface integral E dot ds. Okay. Now I have a question. Where to find out this ds? Sorry, dy dz. Yeah, that's true if it is a rectangular system, because this is a sphere, right? It's a sphere, right? So you go to the table and find out the ds along r direction. Can you go back to your lecture notes and find the ds along r direction? Right. Just go to the table and find out the ds along r direction. Yes. So it should be uh, this thing from table. So r square sine theta d phi. All right. So find ds from the table, and E is given RAR. Now, this means that R dot R is equal to 1, right? So this R and this R is 1. Okay. So A is constant, R and R square is R cube that goes outside, right? So sine theta integration is minus cos theta 0 to pi, and uh, phi integration is 2 pi. Actually, it's 5, but you can directly write 2 pi. You see, this cos 180 is minus 1. Okay. So very careful about the limits. Okay. You see, uh, cos theta 0 to 5. This minus, this minus should be outside. Okay. Keep it outside. Keep it outside. Right. Then expand this cos 180 minus cos 0. So this is minus 1. So minus 1 minus 1 is minus 2. Minus 2 times this, okay, plus. Wait. Please wait. because we have already taken this minus out here. Okay. So okay, now it's correct. It's up to you to take this minus out or keep it here. Okay. Now this is final correction. Please copy this. Now you can take pictures. Delete your previous pictures. Okay, let's take 5 minutes break. Please arrive on time so we can continue. Okay, let's continue. So you can see this is just the demonstration how integration works, right? But line integral is something different. Actually, the solution is similar. Let's say you have this line, right? If you simply do the integration of this function, right, what you get is the area under the curve, right? So there are many methods to do that. Integration is the most, the effective way to do this. So how this function works is that it computes the line segments, right? Actually, there are several line segments, and then you add them together, right? So you can apply this to simply from -2 to 2, this function, and then you can do it. Okay. But I have told you the line integration, right? Or line integral. So you can use the single integral multiplied by some quantity, for example, f dot dn, right? Because the length is not straight, right? Because it's like a curve, right? So you can use this line integral multiplied by this, and then you can find out the work done, right? So work done is equal to this area under the curve, that's line, then you can multiply. Similarly, the area also works like this. In our case, there are several quantities that need area, right? For example, the flux. So we need E vector multiplied by area, but therefore we do double integral. So it works like in similar fashion, right? So if you expand this to triple integral, so that actually computes a 3D surface and computes a small cube inside that region on the surface for the 3D graph. Okay, so that's how the simple the calculus works. So I recommend you, if you like to learn more about like how to compute the surface integrations and how to do the line integrations, you can simply go through the solution or the calculus based small videos to see, right? But we will also solve them when we are doing our problems. So if you need any help, I can explain. So here's another small demonstration about the divergence theorem, right? Remember, we talk about this. So uh, if you see in other subjects, like for example, in physics or in mathematics, so you see that they will write here a simple demonstration. So if you remember, we told you that we discussed that the f or any function here, if it is capital, that means it's a vector field, right? In our case, this f belongs to E, right? So we have an E vector here. So compute the divergence and then take the volume integration. It's exactly same as taking the surface integration and then summing up all the surface integration. Okay. Now, this can be applied to other fields as well. So people use it in mathematics to solve, the volume integration into surface integration or surface into volume integration, right? They call it simple divergence theorem. But in next chapter, we will look at the Maxwell first equation, which is Gauss law, right? And then we will take help from this theorem to solve it. Okay, now let's look at some of the properties. Remember, this is same as you write AXIJK or XYZ, or you write in a column vector, same thing. Okay. So in linear algebra, we usually write in a column vector, right? That matrix notation. So you can use the IJK or XYZ unit vectors or use this method, same thing. Actually, it's just telling you if your vector quantity is along y direction and your area is along x direction, it's zero because x dot y is zero, right? That's what he's telling you. We will only take the direction that is, along with the same direction with the other quantity. So if you remember, we also discussed the work done. So we see different angles, and we saw that work done is highest when the force and the displacement are along with the same direction. That's the physical demonstration, right? So on the left hand side, we have an operator. In mathematics, we call lambda or lambda, but we call it divergence or div. So the divergence of any vector field actually tells you some scalar value, whether it's converging, diverging, or getting constant, right? So if you measure this flux, what is the net flux here, here, here in the small cubes, and then add them together is exactly equal to if you draw several area patches on a volume and measure the flux. It's exactly the same. Technically, it's the same. Now, what's the advantage? Why we should do it? Because of this operator, our large problem can be solved very easily. If you choose the right hand side, you have to solve double integral 6 times, right? Which is very complex. On the left hand side, you just have to apply divergence and triple integral 1 time. So you can save almost 70 to 80% computation that we will see in the next example. Okay, let's solve this, and then we see the importance of this theorem. Okay, now before solving the curve, let's first look at the problem here. Okay, so I would request you to please uh, solve along with me. This is very important. So you see, we are given E. So this is a vector field. Uh, we are asked to find the total outward flux flowing through the surface of a cube centered at the origin with sides equal to 2 units each. That means that we have this kind of a shape, and it's centered at somehow 0, 0, 0, like this, and each side is 2, right? And find out the total flux. So what is the total flux? Total flux is equal to E dot ds. That's the total flux that we are required. Surface integration. Because it has 6 surfaces, so we will solve it 6 times, right? Second part is find out the del dot E integral, right? So we will solve this. I highly recommend you solve this with me. Okay, so we understand each and every step. For a cube, right, 2 centimeter each side has 6 sides, right? So we can write the formula E dot ds. That's the flux. This is equals to F top plus F bottom plus F right. Now you can choose any side as a now E is equals to right. This is your E. Now we should know that This part is called Ex, Ey, and Ez. And this is a vector quantity. Okay. So let's choose F top first. Remember, we are looking for E dot ds. Okay. That's our main target. So we can apply two limits. E dot ds, we use two limits. Two limits on E vector. So E vector is xz minus yz square minus zxy. Okay. That's our E vector. Dot ds. Okay. Now it's up to you to choose where is your top or where is your bottom, where is your left, right. Okay. So you can name anything. Let's say we are taking top as a z plus zx. Of course, bottom should be minus z. But if you replace the name, it doesn't matter. The only thing that you need to consider it, you have to consider x minus x, y minus y, and z minus z. Okay. You have to consider these 6 coordinates. Now, important thing here is because our surface or our shape is cube, right? So its length, width, and height is 2 each. Okay. So it's up to you to choose the axis. Okay. I choose axis like this. So that means that -1 is here, +1 is here. So you can also choose 0 to 2 as well. -1 plus 1 is more like symmetrical. So it solves the integral in much easier time as with respect to 0 to 2. But it doesn't matter. We have both solutions. Okay. Now, so we have two limits now, dy and dx. Because we are choosing positive z-axis. Okay, so this is positive z-axis. And at this axis, the value of z should be 1. Now, can you see xz minus yz square, right? For y and x, we know the limit is from -1 to +1, right? That's the limit. What about the z, right? At this position, because you are considering the top value, right? So the top value, the z is 1, right? For example, if you are at here, this is +1 and this is -1. Okay. So every axis on the top position is at the peak value, and that's one value. Okay. Let me draw the one side. If this is your z-axis, right? So this should be 1. Is okay. So now this is the first equation, and now you can write the rest of the 5 equations by following the symmetry. Now, let's say this is top. What about the bottom? In bottom, we use minus z here, and z should be -1. And that's how we follow to the other parts. Okay. First, solve me this one. Can you multiply this thing and these things? Now this is dot z, right? So x dot z, yes, 0. Y dot z is 0. So these two green lines, the terms will be 0, right? Okay. So that's how you already saw in the video, right? We discussed that uh, if you are considering only one surface, right, the rest of the components will not have any effect because the dot product is 0. So this will cancel out and we will have final okay. So x integration is x square by 2 and y integration is y square by 2. Okay. So if you solve it, you will get x square 1 square minus, you should be very careful when solving the limits. The final answer is 0, right? That means there's no flux in the top surface. Right. So it's up to you. You write f top. Some you can also write like this, f along z direction, or you can also write f along minus z direction. It's up to you. Now we again, one thing you should know that if you are writing z direction, right, only x and y will contribute, right? In minus z, again x and y will contribute because the area is xy. Again, write the same equation. Now z should be minus 1. Can anybody tell me why we have choose z is equal to minus 1 here? So can you tell me why z is minus? Yes, at the bottom, z is minus 1. So we use as a constant value minus because this surface is at minus 1. Okay. Yes. Now minus z and then dy dx. Again, x dot z is 0, y dot z is 0, and minus z is plus z. Okay. So you get a plus and same answer. Same answer. Okay. Because same limits, same function. Okay. So this question looks quite difficult, but when you try to solve it, you can actually solve it by using your own intuition, right? So you can think if, okay, this part is 0, again, same answer, same result, okay? So we saw that when this function of flux enters, then two sides, top and bottom, shouldn't have any flux over there, right? So the flux is 0. Number of field lines, they are 0. Okay, any question from this? Because this question, when we will look at the Gauss law, right, we will use 99% of the same solution. This adds the name, right? When we study the Gauss law, I will change some names only, right? I'll explain it in more application form. So the solution is same. So this type of question for the last 2 semesters, at least 3 months. So after this lecture, we will finish 2 examples. Two examples. Don't wait. When I give you the solution, you will find it. The previous example solution would be exactly same. So the only difference is this part. D dot ds, we will see that Gauss law says that this is actually charge. Only difference. Just add new layer. Take it random. It's up to you. You choose top. So first you use plus d minus d, then you use plus x minus x, then you use plus y minus y. That's it. Gives anything. It's okay. So if you don't like south bottom right, then this side x positive side minus x side. It's fine. It doesn't matter. That's why I like this one. Now we are solving positive z side. It doesn't matter top, bottom, or what. Right? But you should make that the top and bottom are at the z minus z. That's it. Okay. Later, I'll tell you what type of mistakes students make. So you should be very careful about the solution. Now take f along y, we can write it as a right part. Flux on the right side. Again, we will use E dot ds. So x and now if we are using the y part, right, then at y equals to 1 on the corner side, on the surface side. And remember to use y. So these are the changes. These are 3 changes. When you use y, remember to use x and z as a limit, and x and z as the limit of the integration. Okay, so it's more like a symmetrical solution. Okay, so you see now it's xz. So can you see why it's z square only? Anybody? Why it's z square only? Now you see, this is x and this is y. So x dot y is 0. So this is y and this is y. This is acceptable. So z dot y is again cancel out. Okay. So this negative signs comes here. Okay. Now y is equal to 1. So there's only 1 here. Okay. Is this solution clear? Look, y is 1. So this y is 1. This is 0. This is 0 because it's dot product with the y. So the solution is now more simplified. So let's take the okay. So it's a double integral. So I have done it in this form. So it makes it easier for you to understand. So z square derivative integration with respect to x is x z square. So please be careful with the solution. Okay. Now, when you are solving the limits, so majority of the students they make mistake here. That's why the final answer is not correct. So you see, x d cube by 3, right? So 3 is here, this minus is here. X is plus to minus, okay? So x minus lower limit, so that becomes plus. Okay, so it's 2. So z is upper minus lower, z cube minus lower value. So 1 cube is 1 and minus 1 cube is also 1. So this is 2 is 4 minus 4 by 3 is out. Very careful. Now we will f minus y. That one is right. Now we will solve left part. We have the same Remember, previously y is equal to y plus 1. Now we have y is equal to minus 1. Now you see, this x is finished and z is finished. So we would have minus this negative comes out because y is also minus 1. So when you multiply this minus 1 with this minus 1, it becomes positive 1, and plus with this minus 1 becomes minus 1. So you would have, which is exactly equal to the previous question. Okay, so this integral and this integral are exactly same. So we will again write minus 4 by 3. So you can see our answer is this. We have two 4 by 3, minus 4 by 3, and two zeros. Because of this minus and this minus, there is no difference on the solution. Please look carefully and ask if there's any confusion. Okay. Next is f front, which should be positive x-axis. Now the two integrals should be y and z. Again, we write xz. Remember, x is equal to 1. Dot product with x d z dy. Okay. Because of the x equals to 1, you can have positive x here and zy, dz, and dy. These are the area components. Okay. So when you choose x, you choose yz. When you choose minus x, you choose x is equal to minus 1. Okay. So you see x dot x is 1, and rest of them will become 0. So you have xz. You can also short, instead of x, you can write 1z because x is 1. Because of z, first when you integrate with y, you will get yz. Okay. And then when you integrate with z, it becomes yz squared by 2. That's the y limit. And for z, so you see the answer is 0. And this 0 is because of this z square. Okay. Z square means that it turns the negative into positive. That's why the answer is 0. And you will also find f back. So, so this minus and this minus will turn into positive value. Also 0. So you have 1, 0, 2, 0, minus 4 by 3, minus 4 by 3, 0, and 0. So at the end, we can write okay. So that's the right hand side of the divergence theorem. Okay. And now we will find out the other side. First step, calculate del dot E. Please look at this step. This is very important. Please look at this step, the left hand side of the divergence theorem. So now we will find out the divergence and then volume integration. Okay. So first thing is to compute the divergence. What is Ex? Ex is xz. What is Ey? Ey is y z square. And so derivative with respect to x is z and z square and 0. Okay. So that's our divergence. Now plug this divergence in this formula. So first we will apply x limit, then this will become x z minus x z square. Till we have two limits. Then we will apply y limit. We have x y z minus x y z square. Now we have dz limit. Please look at this triple integration. X is uh, that's x. Y is upper minus lower, and z is upper limit minus so this is 2, 2, 0. This is 2, 2. Okay. So you can compare this answer with this one and see that divergence is the most quickest way to, help us find the solution. Uh, I have solved it more sustainable way as compared to the actually you should learn the method. Okay. But for example, I do is sometimes I read the question so simple. So when you do the simplification, it automatically does boils down. But students, please listen. Sometimes students are very smart. So they solve this part and they know the answer. And then they go to the other part and randomly write the answer 2 plus 2, 4, say 4. Right? But actually, those steps are wrong. It is not calculate minus 4 or 3. But they just write randomly 4 or 3 or 6, and at the end they try to make it equal. You understand? So that's why you should be very careful. And another thing, when we study next chapter, we will see that the Gauss statement says that this E dot df is actually the charge density, right? And this part is charge density. So you take the volume integration and get the charge. I will show you that how I make the question. Solution is same. I ask you that okay, you're given charge density, find the charge. So you just do the volume integration. So you can also see in the past paper solution is actually the question is here, but security electric but it's like the other because it's more than this question is lower than please go through it and then continue next topic. So if you have any problem, we can start. Yes. Any problem? Please. Any problem? Okay, so this is our left hand side. So we take the divergence of the E and then try to find out the answer. So first thing is we find this thing. E is already known. So this is the X part. This is Y part, this is E part. We take from E and then take the derivative of X is Z on Y is Z square because there's no Z here. So we take this part here and then take the volume integration. So the volume integration is now this part minus 8 by 2 is equal to the whole sum. So that means you do 1, 2, 3, 4, 5, 6 times. So we have yeah. So this is the surface interior. This is volume integral. So surface interior is difficult. Volume integral is off. So why I'm doing this? Because I want to tell you that divergence is so powerful. So actually, we are still working on this part. So divergence of a vector is easier. And when you do this surface integration, you do it 1, 2, 3, 4, 5, 6 times. So let's say you have Q, you do it 6 times, and then compute the flux. But this operator also finds the flux. So this will automatically find the flux, and then you do the integration. Solution.
Step 2, step 3.
Yeah, this is formula, right?
Formula.
This is the formula. In formula, we need this thing. So I solve this first, and then put this back here.
Put this back.
Yes, then do the integration. This answer is here. Yeah. Then the P is here. The bond dB is called volume integration.
So, and then this.
dB is dx dy dz.
dydc.
No, dx dy dz.
dx.
Yes, have
No.
because here we solve with x.
Oh.
If we solve with x, it's x z x z square. Let me write another step. Yeah. So in the first step, you solve with Vx. So Vx minus x z square because x comes. Then y comes.
Oh, this one is tough.
Yeah, and then z integration is z square by 2. Z square is z cube by 2. You can also make it simple. For example, you can take this common outside. You see, this is square, right? This will make it 0. 1 square minus 1 is 0. But cube cannot.
Oh, this is become this.
Yes, because we have to put two limits, upper limit, lower limit.
Oh,
So this part is here. X
this.
upper limit minus lower limit. Plus 1 minus 2. And then this is for the y part.
Also,
That's what I'm saying. Square terms 0. Cube terms some here.
oh, thank you.
Okay, let's continue our discussion and we will discuss the okay. These because this is the divergence problem that uses the verify the divergence theorem. Okay, so you can verify it. This is for your practice. Okay, so uh, so far we have learned the gradient operator, right? So you apply on a scalar field and answer is vector. Next we learned divergence. So you apply on vector field, you get a scalar, right? So gradient will tell you how a quantity is changing and where is the maximum change. Divergence will tell you, please listen, please listen. Divergence will tell you how much flux is entering or leaving. So measure of flux. Now we have a third quantity that actually tells us, right? So we now try to model the circulation property of vector field. You should know that one of the parameter or one of the quantity that we are interested in magnetic field, right? So because the magnetic field is we cannot apply directly the divergence or gradient, right? So we need another operator that can, right? So this helps us to model the circulation property. So if the component of a vector field is pointing in the direction of a length at any point integral and thus the curl will be positive, right? So what does it mean? It means that if you have some coil here or conductor here or length here, if the length or the flow of the length and the vector field, red is vector field, if they are along the same direction or probably going next to it, then the curl will be positive, right? So it tells us whether the quantity and the field they are along with the same flow of the circulation. If the component are opposite direction, just like this, for example, your length is moving like this and your field is opposite, then this should be a negative value. Okay, so this is somehow similar with the divergence. However, if the both the factors they are somehow in such a position that they actually cancel, for example, uh, vector field will previous definition. You see now? Now they are totally opposite. You see, it's going in this direction, and this is going in this direction, and then this is going this. Some of them is positive, some of them is negative. So the vector sum is zero here, right? Now this could also be the case here. Now some of them are going left, right, and up or down with respect to the distance, right? In this case, it's also zero. The main point here is actually to monitor or find the circulation property. Okay. Now, different from the previous two concepts. In this case, the input is also vector and output is also vector. Right. So gradient. So first gradient. Input is vector. Input is scalar. Output is vector. Divergence. Input is vector. Output is scalar. Curl. Input is vector and output is also vector. Okay, so let's see how we can find something from this. Is a kind of a field. Now you see it's quite different. We have something that is coming out of the conductor, right? Out of the sphere. These are more like electric field lines, right? But now you see they are in the form of a circular loops. Remember, we studied that electric field can be produced from a single charge or from a like charge. For example, if you have a positive terminal here, right, still you have electric field, right? Let's say if you have one conductor, only one potential difference, let's say plus 200 volts, you still have vector field, right? Right. However, if you have only north pole of the magnet, that's not possible. So magnet must be along with north and south pole in terms of a pair, right? If you have a conductor that's the current is flowing inside, then you would see that the magnetic field will be in the form of a circular loops that are continuous. So you cannot break those loops, right? It does not mean that it only have the field on the left side, there's no field on the right side, right? So it should be continuous, right? If the field is like this, then you can actually apply the curl operator to tell you that which part of the field lines are more stronger or more concentric towards the flow of those circles, right? So again, you can plot these type of graphs to see. Okay. So if this scalar, if the component is larger in the region, for example, here, so it's like more like a rotational source. Now remember, previously we were discussing about three different things. Okay. Uh, let's say we talk about so gradient, right? So gradient, the output value tells us the change, maximum change, right? So the peaks, they tells us maximum change where the quantity is changing rapidly. Okay. Divergence, the output is more like a flow, right? That means inward, outward, or constant, right? So the peaks tells us whether there's a source, whether there is sink. Understand? So if there's a source or there's a sink, whether the vectors are converging or diverging. Understand? Now the third thing, curl. Now the output will tell us the peaks that shows circulation. In which part of the field the circulation is more concentric, right? Where it's more stronger, where the circles or the field is more circular, right? So you can see there are three different properties, right? Now you see that at this part, if you have field, this part of the region is more circular. Maybe the circulation is less concentric, and then at the end we have more circular, and then there's no outside the field. Okay, so this is we call curl. It's very difficult to understand the curl following this other demonstration. So we use vector field or the magnetic field because this can be applied on the magnetic field, right, to demonstrate it. Now, can anybody tell me what this demonstration explains to you? Just this figure. What is uniform field? We have discussed this before. This diagram refers to which kind of device or phenomenon. Any idea? Conductor in the magnetic field. This blue line tells you the purple motor, DC motor. Okay, so this is uniform field. That means there are no north and south poles. Field is not changing. So flux is coming from north pole and towards the south pole. That's like a field magnet. Okay, so there is a conductor. So that's actually a coil. Okay, so I'm not teaching motor here, right? We are just trying to demonstrate the circulation. Okay, so we have coil A, B, C, D, A, closed loop. Okay, this length is another because this length is along with the direction of a B, and this length is perpendicular to the direction of B, right? So here is our demonstration. We assume that the DL, what is it? Yes, this is line integral. That's a line integral. The same line integral which we can see from the work done, right? So if you have a uh, 4 force time is the work done. DL is the work done. So if the line is not, you use a limit F dot DL from point 2. That's the work done. In next chapter, we will study same phenomena applied to voltage, right? E dot dl, right? That's voltage. V is equal to dl, right? Remember, work done of a charge against the electric field is potential. Potential is volt, right? You see the volt, 5 volt, 2 volt, 3 volt. It's unit of what is potential. Potential is something work done of a charge against the electric field. That's the potential on your battery, right? So there are three of right? Magnetic field along some direction or the length. Now compute this line integral. So C stands for close. Remember this we saw in the video. This round signal means it's a closed curve, no holes, right? Let's say right. It should be a closed. The point where it starts, the point where it ends. Okay, the integral is not good. It's not correct. Now, do you agree with this formula? Circulation is equal to A to B, B to C, C to D, D to A. Correct? So that's the circulation, complete circulation. Now, what are the quantities B, D, L, right? And you need uh, to put all those formulas into distance. A to B, consider A to B. A to B, right? Uh, B is going to X direction. B is along X direction, right? Because a uniform field, so we write B naught. B is a vector, right? And magnitude is B naught. So this is capital B is equals to right? It's a vector. B naught x. What is the length? The length is this thing, AB, right? So we have a dx length, A to B. What about B to C? So B to C, now magnetic field is actually along x direction, but the length is along y direction. Correct? See, this is y, right? This length is along y direction. Look at the CD. CD is again same, x B naught x dx. Okay, C to D. Now D to A, right? Again same thing. So now you can add them all together, and you will see that the answer is 0, right? 0, right? So now keep this result in your mind, and you see that this makes sense because there is no circulation here. Is there any quantity that is rotating? No. It makes sense that if you take the B dot dl, that's the line integral of a quantity, and add them together with different parts, wherever it is, and go towards the complete loop, this may somehow gives you a sense of circulation. Now B dot dl is 0 for the whole. That means that there's 0 circulation. So now we can take this as a measure of circulation, right? Now come again to another demonstration. Now this is opposite to the previous one. So what is this? Sorry? B field. This field is not from north to south pole. This B field is circular, wide circular current that produces magnetic field, right? So if you pass a current through a conductor, it will produce magnetic field, just like electromagnet, right? So if you take a coil, take a conductor, pass a DC current, and then it will create a magnetic field, right? But the strength of magnetic field is directly proportional to current. We learned in the very first lecture, mu naught I over 2 pi r. So B is the current. The higher the value of current, the higher the magnetic field. Okay. Now, so you have B. Now I want to check on this formula about this B. So B dot dl, what is B? Mu naught I over 2 pi r. Okay. So can you tell me what is dl? Are these circles radius and then resembles? How to find dl on circles? Use cylindrical system. Previous example, we have a rectangle, right? Right? In rectangle, we can use Cartesian system, dx dy. Correct? Can you use dx dy on circles? No. So this is cylinder, right? The blue lines are cylinder, cylindrical axis, right? So now what is the dl? So dl is phi axis, remember, rotational axis, right? So these are dl along rotational. So in cylinder, we have base, like cylinder, we have length along z axis, like, and then we have length along radius axis. So these blue lines now represent dl along phi axis. So r d phi, remember, we have 3 lengths in the cylindrical system. So that's the purpose of teaching you the coordinate systems. So when we are applying any concept on any specific phenomena, we can buy the area from that coordinate system. So you see, in previous question, the length is very simple: dx, dy, dx. It's very simple because that's square, but that comes from Cartesian system. Now the magnetic field is circular. How can I apply the length from Cartesian system? Because it's circular. And length on circular, we learned from uh, the system that it is actually phi axis. That is, yes, r d phi. Now phi dot phi is 1, and then you solve it from the integration in d phi, and then you get 2 pi, 2 pi, 2 pi cancels, and then you have mu naught r cancels, right? So what's the answer? 0? No, it's not 0. What's the answer previously? 0. In 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 square case, right? Circulation is 0, right? You see, we learned in the previous case, you see the field is going here, the field is going here. Number of field line going down and up circulation cancel each other, right? And now this is going here, this is going here, right? So there's no circulation. Field, there is equal and opposite. So in this case, we see the impact is just circular. Now the answer is not 0, right? So we can prove that this concept helps us to measure or sense the amount of circulation in any vector field, right? Now, because we know that in our subject, magnetic field is circular. That's why we use it in magnetic fields. However, in engineering sciences or mathematics, you can apply this to any sort of circular magnetic field, circular vector field, right? It could be a water, it could be molecules, dynamics, airflow, whatever, right? So you see the whirlpool, right? The pressure creates, right? So you can apply it to anywhere. The way we derive this circulation is somehow very tedious, but you should know that the important property is that the curl of a vector field, the input is vector and the output is also vector, right? So because a vector, therefore it has a x component, y component, and z component. And the derivatives are quite symmetrical. For example, for x, you use zy, and for y, you use bx, and for z, you use yx. And in order to remember this, we can use this determinate form, right? In order to memorize it, we can use it. But remember, these type of complex formulas, we don't ask you to remember, right? But for gradient and divergence, you should remember that, right? So if you open the determinant, you would find this one, okay? Now, similar to divergence theorem, we also have a Stokes theorem, right? So Stokes theorems helps us to analyze the circulation of a vector field. It helps us to analyze. Remember what the divergence theorems helps us. It helps us to analyze the flow of electric field, which is what we call the flux, right? How much the flux is entering or leaving. Stokes theorem helps us to see the circulation of a vector field, right? Now, if you want to find V dot dl along length 1, length 2, length 3, length 4, it's going to take long time, right? So for a square or rectangular, you need 4 B dot dls. You need to combine 4 dls, right? But if you can find out the divergence, sorry, the curl of the field, and then you take the surface integration, you can do the same thing. Mathematically, you can solve surface integration problem into a line integral problem. But in the previous theorem, we saw we can solve the volume integration into a surface integration. Okay, so this is another helpful that helps us to switch between line and surface integration. Theorems will help us in our next upcoming two chapters, electrostatistics and magnetostatistics. Okay, so we have two questions for our exam. Okay, so if we finish one or two more lectures, I will give you the the past paper, and then I highlight that okay, these questions come from this chapter. Okay, then you can start preparing. Okay, sorry. Circle. Uh, yeah. Sure, sure.